Hi, and thanks for joining us for Phosphorus Science Now. I'm Matt Scholz from the Sustainable Phosphorus Alliance. We get most of the phosphorus we use from mining it, but that's not its only source. Beyond what's already in the soil, we can find phosphorus within various forms of organic materials, whether those be manure, treated sewage, composts, or other materials. And these wastes are often used for crop fertilization. Doing so takes food system wastes and returns them to the food system in a closed-loop fashion. And reuse and recycling are, of course, pillars of environmental sustainability. But for countries and regions that have dwindling or no real phosphate reserves, in other words, most countries of the world, recycling phosphorus can also be a path to economic sustainability and independence. Where the best opportunities lie for recycling some of these materials is an open question, and one that the current paper tries to address. For this episode, I was joined by Dr. Steve Powers of Washington State University to discuss his recent Earth's Future article entitled Global Opportunities to Increase Agricultural Independence Through Phosphorus Recycling. Steve, thanks so much for joining us for Phosphorus Science Now.
Thanks, Matt. My pleasure.
Yeah, you've had some help writing this article, and I was really happy to see that a lot of the people who are involved in this were actually members of the Phosphorus Sustainability Research Coordination Network that we were in together and that birthed the Sustainable Phosphorus Alliance.
That's right. This is an international collaboration. My home is currently at Washington State University, but we have people from Europe, for example, Jen Metzen. And so another thing to note here for how this got going, Jen and I were co-organizers of a working group supported by the Socio-Environmental Synthesis Center, or SESYNC. We called that Human Dimensions of Phosphorus. So that kick-started this. And Michelle McCracken in Sweden, Dave Vicari, who's on the East Coast. So a truly international collaboration with some multidisciplinary representation to really cool, brilliant team.
Yeah, it's great. Okay, so tell me a little bit about what you guys did.
A little bit of context here. Phosphorus, it's a fundamental, central component of food security and water security, globally speaking. Aspects of this include that the rate of global phosphorus mobilization has surged since the mid-20th century. Second thing to know is that the majority of phosphorus fertilizer that we use to support agriculture, it comes from mines, phosphate rock mines, not renewable sources. Some of us are trying to help change that. And a third thing is that phosphorus leakage from the landscape is polluting water bodies to the point that we can now commonly see algae blooms from space in various parts of the world. So one question that has emerged in research conversations is how can we, and stakeholders too, how can we develop a more circular economy of phosphorus? Connected to that, much of the phosphorus we use, as I mentioned in the last slide, comes from mines in just a handful of countries. China, US, Morocco, and Russia are some of the key players right now, begging the question, whose phosphorus do we want to depend on in the foreseeable future? Another thing that's going on is livestock production is on the rise globally, and with that comes more phosphorus-rich manure. And we're still figuring out what to do with all that phosphorus, and often there's a disposal mentality that is counter to this circular economy idea. So there are ways that we can recover phosphorus from agriculture and also urban systems, for example, biosolids, more effectively, and reuse it, ideally, the same atoms, phosphorus atoms, over and over again. And one thing I want to emphasize is that the data underlying this global analysis are shared, the derived data sets that we put together. It's shared in a public repository called Pangea, so check that out if you have a use for the data or want to know more about what's going on under the hood. And also the article itself is open access.
Great.
in Earth's future. This work got some attention recently, and some curious things happened there. One representation of that is this headline: "This global map of manure could kickstart smarter phosphorus use and help save agriculture as we know it." I did not write those words, but I did generate the map, and I can promise you that a single map will not solve a complex global problem like how can we sustainably produce our food. But it's cool to see these things getting attention and fueling conversations. Just in this work alone, there were several maps that we put together to understand the associations. And by the way, beyond maps, we need people all over the world pushing for ingenuity towards sustainable agriculture, supporting innovations, not just keeping the status quo. So this work also is not just about manure, even though that's an important piece.
Sure. And so what were your research questions, Steve?
We had 2 questions, and they involve understanding associations between manure and crops, as well as people and crops, the co-occurrences of those things. So first question: how are manure-rich and populous cropped areas distributed globally? What does that map look like at a pretty fine resolution? And secondly, how do these presumed hotspots for recycling potential overlap with fertilizer import dependencies at the national level? Where does that come from? It connects back to the reality that many countries are reliant on phosphate rock imports and fertilizer imports from overseas due to a lack of native mining and deposits within the country. Much of our analysis centers on 3 core globally complete data sets. The first is a global map of croplands. We used something called globe cover, which focuses on patterns in cropland in the late 2000s, as of the late 2000s. At the bottom, human population density, and then new calculations in the middle on manure phosphorus. For that, we use something called the gridded livestock data set of the world, but we combine that with estimates of excretion factors, phosphorus excretion factors by various animals, cattle, sheep, goats, pigs, chickens, to come up with a new global map in red of manure phosphorus. And then, armed with these 3 maps and a few other supporting data sets too, we sought to understand the intersections and, in short, where the hot spots for phosphorus recycling, or at least recycling potential, might be. And a bit more detail on the data sets here. So it's not just about manure. We also incorporated the nation level story and calculated something called the fertilizer import ratio, which it's an indicator of how dependent a country is on phosphorus fertilizer from the outside. So where are the global hotspots for manure, the manure side of the equation? To get at that, we generated a map where green areas are places where we have the highest manure phosphorus and some of the highest cropland extents in the world. Okay, and you see a lot of green in places like India, Eastern China, Argentina, and parts of Brazil, and also the Central Plains, Western Plains of the US. These are not the only areas, of course. These are locations with very high phosphorus throughput going on, and co-location within a reasonable distance, say 10 kilometers or so, co-location of manure phosphorus and croplands where one can imagine that would be a smart place to ramp up recycling effort. And another thing I want to point out in this map is areas in blue We interpret those as places that likely have manure phosphorus surplus because there's less cropland in those locations, begging the question, what are we going to do with all of it? Can we recover it and ship it out further to places where we do have croplands? There are costs associated with that.
Yeah, it's great. And you have something of a video demonstration for us of the tool?
Yeah, I do. And so along with the data being shared, we have a data viewer associated with this. So there are all sorts of ways, even for a single data set, that we can map that single data set in different ways. So if anyone watching this is interested in a particular part of the world, and not necessarily the whole world, this data viewer might be of some use to that, because you can explore specific countries. There are multiple resolutions in the analysis we conducted, and there's some representation of that in the data viewer. A lot of information to work with here and different ways to adjust the color schemes and see what the stats are for a given location. So check that out. There's a lot more that you can learn in there that we didn't have the space to write about in a pretty short research article. And then going back, I showed the manure and cropland map on the top. We also generated a companion map that shows where people in cropland are both present. Green being the places where we have the highest densities of people in crops worldwide, the 90 percentiles or higher. And it's a similar map, but not exactly, right, to the manure. And so one thing that's going on, if you look in the Americas, there's less green in the people and cropland map compared to the manure and phosphorus. We interpret that as a sign of spatial segregation of people and crops, more spatial segregation in the Americas compared to manure and crops. Not the case, however, for India, Eastern China, parts of Africa and Europe. So these are patterns that, to a certain extent, geographers know and have been helping on, but we're providing a more phosphorus-centric angle on it at the finest resolution that I'm yet aware for a globally complete analysis. And shifting to the national scale, lots of folks have been working on nation-level analyses and substance flow analyses of phosphorus and fertilizer. This often involves FAO data, FAO stat. And so we sought to confirm some of the things we thought we already knew about the nation-level patterns, and effectively did that. What we're looking at here on the x-axis, this is a standardized, rescaled measure of the nation-level fertilizer mass consumption annually. So on the right, we have the biggest consumers: China, USA, India, Brazil, Australia, etc. And on the y-axis, this is our fertilizer import ratio that we calculated, a measure of the dependency on fertilizer or phosphorus from the outside. And what you see is a big spread. And many countries, for example, a lot of countries in Europe, but not only that, are well above 0.4 or 0.5 import ratio. And if you have an import ratio of 1, that means the net fertilizer phosphorus that you import is equivalent to what you consume. In simpler terms, pretty high import dependency. And so, armed with those calculations about import dependency, we went back to the maps and decided to count up which types of countries had which types of hotspots for recycling potential. And one of the things we found is that many of the hotspot areas for phosphorus recycling, both from manure-rich cultivated areas and populous areas, many of those were located in countries that simultaneously have a pretty high import dependency on phosphorus fertilizer. So an argument can be made that those hot spots for recycling potential or right where we need them from a agricultural sustainability standpoint, and also from an agricultural independence standpoint, perhaps. At the same time, and we saw this in the earlier maps, India and China both have a large share of both types of hot spots. Again, these are lands that have more than 90, they're above the 90th percentiles for the global distribution of manure and croplands, so really hot spots. But some interesting intricacies involving other nations like Brazil, and some details that I'm not sure we have enough time to go into in this presentation, but check out the paper if you want to know more. Oh, another thing I meant to say before we move on is that colored here at the right, that's the recent trend in nation-level fertilizer use since the mid-2000s. So, for example, areas in red are countries that had the highest increases in nation-level phosphorus use. So those are places where things are changing. Demand for fertilizer is going up. Why not use some of the recyclable fraction to support that rather than ship fertilizer across the oceans? It's something that these countries might want to consider. So here are these maps again. I want to emphasize a few of the main points from the article. One, that many nations import mineral phosphorus fertilizer for agriculture, but what we showed is that a lot of those nations possess alternative local recyclable phosphorus in the form of livestock and very likely abundant biosolids associated with human excreta and wastewater treatment. A second main point, the global analysis revealed where the manure-rich and populous cropped areas occur, and by extension, where recycling potential may be highest. Third, abundant phosphorus recycling opportunities exist in countries that have traditionally relied on fertilizer imports from abroad or have had recent rises in fertilizer demand. And we've argued that by recycling the phosphorus that's already there, that's a pathway towards more agricultural independence.
Steve, did you actually figure out the percentage of phosphate demand that could be met by recycling these materials, or is that for future work?
I haven't gotten there yet. That would be a logical step for future work. One thing we did do is compare the estimates of manure phosphorus versus urban phosphorus, using some assumptions about how much P we generate in human excreta. And what that confirmed is that in a lot of places there is far more manure phosphorus, commonly 8 or 10-fold, at least at this grid cell resolution, 8 or 10-fold more compared to the urban P. But it's spatially variable, right? And there's no silver bullet when it comes to phosphorus recovery and recycling. We need to explore multiple pathways and be mindful of the local and regional contexts. And these are some of the supporting reasons for why we bothered to generate these kinds of maps. Another important area for future work, though, is the time component. We need to keep tracking these sorts of things, keep revising the global maps in accordance with emerging data sets, because things are changing very rapidly in certain parts of the world.
Great, Steve. Well, you've given us a great framework for thinking about these things, and other people will certainly build upon what you've done. Thanks a lot for joining us for Phosphorus Science Now.
Thanks so much, Matt.